Okay, let's start. We already come to the very last chapter, which we can definitely finish in this week. Yeah. We are now setting the exam papers. Actually, the question already settled. So now I'm in the procedure to simplify the computations. Our aim is to make sure that you understand the procedure, the basic concepts, rather than the very tedious computations. Of course, computation is necessary. Just last week, we received a message say now the use of the calculator. There are only three options, namely no calculator means none of them can be used. Yeah. So and another one is say you can use non-programmable calculator. And last one is no restriction. So for this case, right, of course, I don't think that you prefer to have something very fancy. Of course, we can easily set the question so that calculator will be useless. You can refer to most of them, my books in my office. Most of them doesn't require any computation, just the concepts. Yeah, but I hope this is not the case. On the other hand, calculator, I think, is also easy for you to do the computations. But the thing is, so how do we distinguish the graphing calculator and the programmable calculator? Any idea? Okay, many years ago, okay, there may be some graphing calculator which are not programmable. But recently, okay, last week we searched for the models in Google, but we realized that at least for the new models, graphing calculator equals to programmable calculator. All right, so just bring the common one, the scientific one will do. If you bring any graphing calculator, you need to prove yourself that it is not programmable. We'll search for the model. If we find that this model is actually programmable, okay, we'll temporarily keep your calculator. You have to do the exam paper without any calculator. So if you are sure that you can get a very old model of the graphing calculator, up to you, but linear algebra, we don't need to draw the graphs. Okay. So my suggestion is, okay, still get a very common one, the scientific calculator will do. Yeah. And also, so scientific calculator, make sure that it works. Okay, say if in case of no battery, it is your responsibility. I know that it happens. Okay, in the past 10 years, I think it happens one or twice. So make sure that check your calculator, which can work properly. Of course, without use of the calculator, you can still do your works, which I promise. Okay. So now let's continue with the linear transformation. This is just the collection of the notions from the past 6 chapters. For linear algebra, okay, the name is linear algebra. So in each branch of the mathematics, okay, we have two things to study. One is the objects, and another is the relation between the objects. For example, you learn so-called calculus. So what are the objects? The objects are the real numbers or the intervals. So what is the relation between them? The relation between them are the functions, usually the continuous or differentiable functions. So this will be the relation between, in calculus. So we need to have the objects and the relation between the objects. Formally, in mathematics, the relation we call morphisms. Then in linear algebra, what are the objects we study? Vector spaces. Okay, the vector spaces are the objects that we study. Of course, inside the objects, okay, there are vectors. So now we are looking for the relation between two vector spaces. Of course, this relation needs to satisfy certain criteria. which are known to be the linear transformations. But, okay, this is just the starting point because, okay, we spent 6 chapters, almost the 1 semester to study the vector spaces. Then only left with 1 chapter, so we just want to have a very brief description for the linear transformations. Okay, more topics will be in following courses if you're interested. Yeah. So now for here in this chapter, we'll only study the linear transformation, see the relation between very special vector spaces, namely the Euclidean spaces. So what is that? Let's look at the notes. Okay, so our focus is just the linear transformation from the one Euclidean space to another Euclidean space. Okay, so first of all, let's recall what is a linear equation. A linear equation, right, must be an equation first of all, right? So it has the following form: a1x1 plus a2x2 plus until the anxn equals to b, right? So for that case, a1, a2 until the an and b, they are constants, x1, x2, until the xn, they are the variables, okay? So this is just a convention. So for this case, we say the value of the left side of the equation to be a function. And we check for what values of x1, x2, xn, the value can be b. Right, so the left side, a1, x1 plus the a2, x2 plus until the an, xn, this is a mapping, or you can say it's a function. They're the same thing. Mapping, function, they're the same thing. Okay, so here I just use the mapping. If you don't like, you can change to functions. So the left side of the linear equation is just a linear function, right? This is, to be more precise, a linear transformation from the Rn. Rn is the domain. You know what is the domain? Domain is the collection of the point on which the function is defined. And R, this R is, okay, not the range, R is so-called the codomain, right? The codomain. So it doesn't mean that everything can be matched. For example, okay, we have MA1522 students. Okay, this is my set of the students, right? And now I have a function, right? What is the function? Here, right? A plus A until F, right? So this is my function. So it can be my function, right? So every student will be assigned to a grade at the end of the semester. Of course, okay, may still be something so-called the incomplete, okay, withdraw or something, right? But assume that everyone take the have it, okay? So, but it doesn't mean that every grade must be taken. For example, I hope that no one can F. Actually, possible, quite possible, as long as you do something. Okay, so it's very hard to get F, honestly. I mean, so as long as you do the homework assignment regularly, as long as you study regularly, you say, okay, I try my best, I still fail. No way. Okay, no way. Trust me, no way. Nowadays, no way. If you really try your best, not say to try best, if you try and you fail, no way. Of course, it's also possible that no one get A plus in case everyone did badly. Right, so it doesn't mean, it means that, okay, not everything here will be matched, but this is so-called the codomain, correlative domain. Yeah. So we say this is the linear transformation from the Rn to R, just write the notations. Okay, where the number come from, they are the domain, right? So from the Rn, where the value goes to R, the set of the, okay, codomain. Of course, this is the linear algebra. So if we want to represent in the matrix form, very simple. Okay, so here, although I don't really like the notation, but at the beginning, right, we still have to use it. Okay, to be more precise. Okay, the a1x1 plus a2x2 until the anxn, of course, can be written in this form, right? So the row vector times a column vector. Okay, then on the left-hand side, right, so many brackets, yes. Because the bracket inside, this is the bracket for the vector. Okay, this is the bracket for the vector. And here, this is the bracket for the function. Okay, but this is just the starting points. In the future, when you study more, you can omit some of the vectors. You can omit some of the brackets. For example, with or without the brackets, if you write the numbers in such a way, it is a vector, right? For example, just to say that you input these numbers in Excel. Whether you put the boundary or not, it is still a collection of the data, and there is no mistake when you do the computation. But we put the bracket just to emphasize that this is a vector, just to make sure that it can look nice. That's it. All right. So here we have two brackets. But just to be honest, for example, in the exam or in the assignments, right, you omit some of the bracket is fine to me. But I need to write properly. Okay, so this is about the metric form for the linear transformation. Right, in this chapter, all the vectors will be viewed as column vectors for the computation purpose because it is about the matrix multiplication. Yeah. Okay, now what happens to a linear system? Linear system is just a collection of the linear functions which has the following form, which I copy from chapter 1. Okay, so we have m equations in n variables, where the a, I, j, b, I, they are constants, and x1, x2, xn, they are the variables. So here we have a metric. So here I now use the t. You can use other notations, but usually we prefer to use t. For what reason, I have no idea, but t. T transformation, t. So t is a function from Rn to Rm. Why not Mn, but Nm? There is a reason we'll see later on. Yeah. So now we just need to put together. Instead of just the 1 and 3, we have so many entries, but they are written in columns. So this is, again, right? Again, this is the bracket for the vector. The outside one is the bracket for the function, right? So we have the matrix form. Okay, we have the function in such a form, right? So from the Rn to Rm, there are n vectors, n components. Here there are m components. But it's very clear, right? We see that it can be written in the matrix form, which we study in chapter 2. Right? It is known to be a linear transformation from Rn to Rm, which is, okay, this is the linear transformation. Of course, it can be written in the matrix form. Later we'll see. This is a linear transformation, right? From the Rn, there are n components. Here, Rm. So each of the components must be a linear function. In particular, if the m and n are the same, so we have a special name. Of course, you can still say it is a linear transformation from Rn to Rm, but it is known to be a linear operator. So for such case, you can take the composite by itself. Yeah, linear operator from 1 to itself. Okay, a linear transformation can be written in the matrix form. Just now we see, right? So the other side, okay, this part definitely can be written in the matrix form, right? We see in chapter 2. So this is a vector. This is a matrix, which is the coefficient matrix of the linear system, right? And this is also, again, the variable. So therefore, right, if you use the A to represent this n by n matrix, right? That's why we use n by n, m rows and n columns. And x is a column vector in Rn. So this linear transformation is representable in the form of Tx equals to Ax. So this A is known to be the standard matrix for T, which represent the linear transformation. So what is the linear transformation? Linear transformation is a function between the Euclidean spaces so that each component is a linear function. On the other hand, right, a linear transformation is just in terms of the matrix multiplication. So we need to have a matrix A so that every Tx can be written in terms of the Ax. So this is linear transformation, which is essentially a matrix multiplication. Okay, so let's see some example. So now all the linear transformations, okay, most likely if it is more convenient, I will use the matrix form. Okay, let's consider the linear operator. from the Rn to Rn. This is the simplest to say, no matter which one I have, I just send to itself. Right, this is the linear operator from Rn to Rn. And this is known to be the identity operator, something like the identity function. Okay, this is actually linear. Why? Because you can see Ix equals to x, but x equals to the identity matrix of order n multiplied with the x. So therefore, right, this function can be written as a matrix multiplied with x. So therefore, we can say it is a linear transformation and the identity matrix is the standard matrix. Right, as long as the linear transformation can be written in AX, right, TX can be written as AX, it is a linear transformation. If it cannot be written in such a way, it is not. Okay, then for example, right, O, I use O in some sense is our zero, right? So now we don't need the domain and codomain to be the same. O is a mapping from the Rn to Rm, such that no matter what is the input, the output is the zero vector in Rm. This is known to be the zero transformation. Okay, clear? And zero transformation. Zero is, of course, the zero matrix multiplied with the zero vector. But what is the order? Right, initially, this is the zero matrix. This is the zero in R and M, right? It is supposed to be written as the zero matrix multiplied with the zero matrix in the domain. Domain is in Rn, right? This is in Rn. So when you multiply, right? I want to get a matrix. So I must make sure that the number of the column is the same as the n. This is the n. Now after multiplication, you have a vector in Rn. So this is n by n. Right? The size must be matched. So indeed, you can read from here. If there is a function from the Rn to Rm, this matrix must have the size n by n. So therefore, the zero matrix is the standard matrix for O, right? So it makes sense. And suppose T is any linear transformation from Rn to Rm. Now we want to know. Of course, we can write down the standard matrix. Is the standard matrix unique? Is it possible that I can have another matrix so that the linear transformation Tx can be written as the Ax, and meanwhile, it can also be written as the Bx. If this is the case, we cannot say the standard matrix. We can only say a standard matrix. Is it possible? Of course, we want the answers to be consistent, right? So is it possible? Let's see. Suppose we have a linear transformation so that Tx equals to Ax and Tx equals to Bx. What I want to see is A and B are actually the same thing. Now, a few ways, right? They are the same, so the difference is zero. So in other words, no matter which x we have, zero is always Ax minus the Bx. And by distribution, this is, okay, the bracket A minus B times the x. So no matter what is the x, right? A minus B, this is a matrix. So maybe I say C equals to A minus B. So Cx equals to 0 is the same to say x belongs to any Rn. So what does it mean? What is the collection of all the points so that Cx equals to 0? This is nothing but the null space. So null space of the C, which is the A minus B, is, okay, the whole of the Rn. Right, the null space, right? So the null space of the C is the whole of the Rn. But what is that? So what is this? So the nullity is the dimension, right? The nullity of the A minus B is the dimension of the Rn equals to n. This is the nullity. Now what is the rank? Rank is 0 because A minus B is, right, n by n. N is the number of the columns, right? So the nullity equals to n means the matrix is 0. Or we can say the rank equals to 0. So this matrix is the 0 matrix, right? A minus B is the 0 matrix, or we can simply say A equals to B. So you are free to say that, okay, the standard matrix is unique. As long as you are given linear transformation, you must have only one standard matrix. Different people must have the same solution, not the same as the basis, right? You may have different bases for a vector space, but dimension must be the same, right? So this is, you may have different ways to write down the linear transformation and in terms of the function. For example, instead of the ax plus, instead of say, for example, 2x plus y, you can write as x plus y also can, right? But in terms of the matrix, it is unique. Or alternatively, actually, there's another way to do it. Since we say, okay, remember, given a vector space, in general, there are infinitely many vectors. So what is essential? It is the basis. We are more interested with a basis rather than every vector in the matrix space, in the vector space. So it is already given that for every vector x in Rn, right? Tx can be written as ax, tx can be written as the bx. So let's try to use some special x. And the simplest the vectors in Rn will be the standard basis, E1, E2, En. For example, in R3, remember, E1 is, okay, everything in column, so it's the 1, 0, 0. E2 is 0, 1, 0, and E3 equals to 0, 0, 1. Right? So we can have AE1 equals to BE1, right? Because they are both the T of the E1. Similarly, AEN equals to BEN. But what are they? We already know this, right? A, okay, what is the AE1? The first column of the A is E1. To be more precise, A equals to A times the identity matrix. Identity matrix is the matrix. First column is E1, second column is E2, last column is En, and we know that we can decompose the matrix multiplication in such a form. The first matrix can be decomposed in terms of the rows, and the second one can be decomposed in terms of the columns. So this is first column AE1, second column is AE2, last column is AEN, right? So AE1 is just the first column of the A. AEN is the nth column of the A. So which can be written in this form. But AE1 is the same as the BE1. AEN is the same as the BN, so I can rewrite in this way, right? It is the same as the matrix. The columns are the BE1, BE2, BN, but this is the first column of the B. This is the last column of the B. If you put together, it is nothing but B, right? So for that case, we don't need to see, right? It is true for all the X. We just need to see that, right? It is true for the standard basis, E1, E2 until the En. So this is another way. So for any case, right, the conclusion is the standard matrix for any linear transformation is unique. You cannot have any different standard matrix. Okay? Why standard? Because it is obtained from the standard basis. Right? So the standard matrix now you know, right? It is just the image. This is the TE1, this is the TEN, which is formed by the images of the standard basis. That's why we call standard matrix. Yeah. So now the question is, how do we show that a T is a linear transformation? Of course, someone read some other resources. There are alternative ways to define linear transformation. But for this case, right, we just use our very simple notion. Okay, it's the first us to find matrix A. This is our definition. We just need to find the matrix A so that this function can be written in the form A times the X. As long as this is true, then the T is a linear transformation with the given standard matrix. So for example, right, suppose T is a mapping from R2 to R3, which is of the form. T will send the vector xy to the vector x plus y, 2x minus 3y. You can see that each of the component is a linear function, x plus y, 2x minus 3y. So we can write properly. If the coefficient is 1, you know that we don't need to write this, right? If the coefficient is 0, the term will disappear. So let's rewrite it as The first row, 1x plus 1y. Second row is like 2x plus 0y. Third row is the 0x minus 3y. So which can now be written in the matrix form, right? So the matrix is 1, 1, 2, 0, 0 minus 3, right? Multiply with the xy. So this mapping can be written as T of a variable equals to a matrix times the variable. So therefore, this is a linear transformation, and moreover, we know what is the standard matrix. Say the standard matrix is given as follows. And indeed, you can also see, right, if it's a linear transformation, the first column, 1, 2, 0, it is just the image of the E1. What is the E1? So for this case, is the, 1, 0. So you plug in the x equals to 1 and y equals to 0 is the 1 plus 0, right? 2 times 1 and minus 3 times 0, which is the 1, 2, 0. Similarly, TE2 will be 1, 0, minus 3. But you cannot do this before you verify that it is a linear transformation. Right? If it is a linear transformation, then it is true. Otherwise, you cannot do. Right? You cannot say, oh yes, I find the TE1, I find the TE2, so it's a linear transformation. No, you need to verify this is the form. Maybe I can just show you a very simple example. Just say, T of the, just say T of the xy. Very simple, just equals to, 1, 1. Then can I say that, T of the E1 equals to 1, 1. T of the E2 equals to 1, 1. Then can we say that T is a linear transformation so that the standard matrix equals to 1, 1, 1, 1? Of course, no. Right? So you must first verify that it's the linear, then you can use this formula. Just the same say, you must make sure that you are a student in MA1522. Then we can discuss, how do you get the A for the course, right? So this is the case into write the linear transformation in the following form. A matrix multiplied with the variable matrix. Okay, now let's see the property. Just now is a very simple case. You want to show that some mapping is a linear transformation. But how do you show that a mapping is not a linear transformation? The same as the matrix space, the same as the vector space. Right, we need to verify some basic property for the vector spaces. Then if we see that any property is contradicted, then that one is not a vector space. For example, vector space, 0 must be there, it must be closed under addition, it must be closed under the scalar multiplication. Then the same for the linearity. For the linear transformation, we need a property which is going to be the linearity. So suppose we have a linear transformation, right, from Rn to Rm. Then if A is the standard matrix for T, we can verify, so this is the definition, Tx equals to Ax for every x. So we verify something. Still again about the 0, still about the addition, and also the scalar multiplication. Let's see what happens. Because for vectors, these are the essential things. First of all, T0. T0 is of course A times 0, which is 0. So any linear transformation will send the 0 vector to the 0 vector. If this is not the case, T cannot be a linear transformation. For example, just now the example that I see, right? For this case, no matter which one, so T of the 0 will still give you 1, 1. So this is not a linear transformation because any linear transformation must send the 0 to 0. Of course, here, this is the 0 vector in Rn, this is the 0 vector in Rm. These two 0 are not necessarily the same. Right? Now, how about the scalar multiplication? P of the linear transformation applying to CV. Right? By definition, this is the A times the CV, and this C we can bring outside, which is the C times the AV. Well, the AV is just the T of the V, right? So what does that mean? It means that the linear transformation, we can bring the scalar outside. So we can bring the scalar outside the linear transformation. Right? Something like, for example, differentiation, Right? If you have a function, right? If you differentiate. Okay, T you can review as a differentiation, right? This is the C times the derivative of the same. Indeed, differentiation is linear. Okay. Anyway, so we can bring the constant outside, right? Now how about the sum? T of the U plus V, this is the A times the U plus V. Now for matrix multiplication, we have the distributive law. So this is the AU plus the AV, which is the TU plus TV. So you can also split the sum. Also, this is the same as the differentiation, right? Dx, right? So differentiate the F plus G. This is the derivative of the F plus the derivative of the G. In the future, you'll see that differentiation is also a linear transformation. But the vector spaces are different. Yeah. Anyway, so the linear transformation will satisfy the following three conditions. And more generally, if you have a collection of the vectors in Rn and a collection of the real numbers, then if you consider the T applying to this linear combination, what can we say? Of course, again, by definition, this is the A times the linear combination. And now we can distribute the A inside, right, and bring the coefficient outside. Now each of them, AV1 is the TV1, AVK is the TVK. So this is the linear combination of the images. So we can say, right, the first one, T will send the zero vector to the zero vector. T will send the scalar multiple to the scalar multiple of the image, right? The image of the scalar multiple is the scalar multiple of the image. The image of the sum is the sum of the images. And more generally, the image of the linear transformation is the linear transformation of the images. Right? So this property is known to be the linearity of the linear transformation. So just a conclusion, right? So let T be a linear transformation from Rn to Rm. Just a summary. So T will send the zero vector to the zero vector. More precisely, T will send the zero vector in Rn to the zero vector in Rm. And if you have a collection of the vectors in Rn, collection of the real numbers in R, then T will send the linear transformation to the linear transformation of the images. Right? You can split the sum and bring the constant outside. In some sense, for differentiation, right? The teacher told you, right? You can differentiate term by term. Okay, by the way, integration, you can also do the same thing. Integration, you can also integrate term by term. So essentially, they are the same thing. And now suppose E is, in particular, suppose E is the standard basis for Rn. Right? Remember, every vector V equals to C1, C2, Cn. So this is also the coordinate vector of the V relative to E. Right? This is the standard basis. So it can be written in the form C1 E1 plus until the Cn En. So if you know the images of the TE1, TE2, TEn, now we are ready to write down the TV. Say suppose T is any linear transformation. So TV can be written as, right? So V is the C1 E1 plus until the Cn En. Now using this property, this is the C1 times the TE1 plus until the Cn times the TEn. So as long as you know the images of the TE1 until the TEn, then you know the images of all other vectors. So again, we pay more attention with what happens on a basis rather than every general vector, right? So we can say informally, right? Say the TV is completely determined by the TE1, TE2, TEn. So if it is given to be a linear transformation, we just need to know what happens on the standard basis. Then the linear transformation is completely determined. We don't need to deal with so many, infinitely many vectors. We just need to pay attention on the basis. So that's why we want to study on the basis. Okay, now let's see more properly. Right, suppose T is the linear transformation with the standard matrix A, how the A is constructed. Right, remember? TV equals to AV. So essentially, they are the same thing. Linear transformation between the Euclidean spaces is the same as the matrix multiplication. So in particular, TE1 equals to AE1, which is the first column of the A, right? Agree with just now what we observed. Until the TN equals to AEN, which is the last column of the A. So this is the A transformation. AI, I is the matrix. First column E1, last column En, right, which can be written as, right, AE1 until the AEN. So first column of the A until the last column of the A. And this is precisely, right, the images. First column is the image of the E1, last column is the image of the En. So this is the more formal way, right, to write down the standard matrix. If the T is given to be a linear transformation, now you just need to evaluate the images at E1, E2, En, view them in column vectors, and then you can form the matrix. This matrix is the standard matrix for the linear transformation. Right? So for example, right? If you have a linear transformation, it must be given as a linear transformation. It is given so that the T of the E1 equals to 1, 2, 3. T of the E2 equals to 4, 5, 6. Then T has the standard. This is a standard matrix, right? Say the first column is 1, 2, 3, and the second column is 4, 5, 6. Okay, which is hopefully straightforward. And now suppose, right? So this is one way, right? This is one direction. Say if T is a linear transformation, this condition is fulfilled. Now, conversely, suppose we have just a random function or random mapping from Rn to Rn, such that, right, it satisfies this so-called linearity. Can we say that T is a linear transformation? Yes or no? Okay, let's see. Indeed, okay, we guess that it is a linear transformation. How do we show that it is a linear transformation? We need to get the standard matrix. And how do we get the standard matrix? If this T is a linear transformation, the standard matrix must be given in this form. So let's verify whether this matrix is the linear transformation. Or in other words, whether if you write the A in such a form, first column the TE1, second column TE2, last column the TEN, whether my TV can be written as the AV. Yes or no? This is the verification. Because if it's a linear transformation, this must be the standard matrix. So again, the same just now, right? Every vector in Rn, it is of the form C1, C2, Cn, which can be written as a linear combination of the vectors in the standard basis. So using the linearity, right? TV, V is this matrix, this vector. So using the linearity, this is the C1 times the TE1 plus until the Cn times the TEN. But this, you can see, we have n pairs of the numbers, multiply component-wise and add together, so which can be written in the matrix multiplication. A row vector times a column vector. No, sorry, no, not row vector. A matrix times a column vector, right? A matrix times a column vector. This is the linear transformation, right? So column vector. So a linear transformation of this. These are vectors, sorry. These are real numbers. So now we can see, right, we put these vectors in columns and put the matrix, and the coefficients C1, C2, Cn, we put in the columns. So this can be written in the matrix form, which we see in chapter 3, right? Everything. So what is this? This is my A, and this is my V in the column form, right? So therefore, my TV equals to this one, which is the V, and which is the A times the V. So yes, if T satisfies the following condition, then if you write the A in this matrix, I have my TV equals to AV. So which says that the T is a linear transformation and A is the standard matrix of the linear transformation. So they are now equivalents, right? A function is a linear transformation if only it is linear. it satisfies the linearity. Right? T will send a linear combination to the linear combination of the images. So now, if you want to show that a linear transformation is not if you want to show that a function is not a linear transformation, you just to show that this condition is not fulfilled. Right? So I just write down the theorem. So suppose T is a function, right? A linear transformation. T is a linear transformation if and only if it is linear. If and only if, satisfy the linearity. And in particular, the linearity, linear combination is just linear combination is just successive operations on the addition and the scalar multiplication. So as long as you can verify that, right, say this property for scalar multiplication is fulfilled, T will send the scalar multiple to the scalar multiple of the image, and T will split in such a case, say T will send the sum to the sum of the images. Roughly speaking, you can do term by term. So as long as these two conditions are fulfilled, then T is a linear transformation. And conversely, if T is a linear transformation, these two conditions must be fulfilled. So here we have the clearer property to see whether a mapping is a linear transformation or not. Right? So just now we already see. How do we show that the mapping is a linear transformation? Right? Just need to find the standard matrix. You may say, okay, is it possible that I can use this theorem? I verify that this is true and also verify that this is true. Yes, but not recommended. The reason is very simple. Usually the verification is more tedious and which is more general for other kind of the vector spaces. Right? Why would be more tedious? And if you just say, okay, verify to try to find the A so that the TV equals to AV. This is the simplest because usually I will not only ask you to find the to check whether it's a linear transformation. I will say if it's a linear transformation, find the A for me. Okay, so this is essential. So although you can use the theorem, but it is not recommended if you want to show that it is a linear transformation. I say you can do, but not recommended. I will not stop you to do it, but I suggest not to do it that way. Only when you show that a mapping is not a linear transformation, now you consider this. Okay, the same as something like the vector space. Of course, T will send a 0 to 0, although it's not included, but you can verify easily, right? So to show that T will not send a 0 to 0. Or say you can find a pair of vectors and constant, right? So that T of the CV is not the same as the C times the TV. Or you can find two vectors, U and V, so that T applying to the sum U and V is not the same as the TU plus TV. So as long as any one of the conditions is not fulfilled, then this T is not a linear transformation. Right? So just say some examples. The first example, right? T1 will send the xy to x plus 1 and y plus 3. Is this linear? Now you can see. This doesn't seem to be a linear function. Right, by means of the linear function, it must be some x plus some y plus some z or whatever. Okay, no constant. Since there are constants, non-zero constants, this is not supposed to be linear. But how do you show? Okay, the simplest way is to check on the zero vector. T1 applying to the zero vector, just replace the x and y by 0. So what we have is 1, 3. Of course, 1, 3 is non-zero. So immediately you can say that T1 is not a linear transformation. Okay? Now alternatively, of course, the way is not unique. For example, you consider, for example, T1 applying to twice of the 1, 1. So 2 is the constant and 1, 1 is the vector. Of course, this is the T1 applying to 2, 2, 2 times 2. Now you can see the importance of using the bracket, right? So, T1 applying to 2, 2. So just say this is your x and y both applied, replaced by 2. So 2 plus 1, 2 plus 3, which is 3, 5. But on the other hand, right? Twice of the T1 applying to 1, 1. T1 applying to 1, 1, so just the 1 plus 1, 1 plus 3, which is the twice of the 2, 4, which is 4, 8. Clearly, these two are different, right? T1 applying to twice of 1, 1 is not the same as the twice of the T1 applying to 1, 1. So therefore, T1 is not linear. Any one of them will do, but 0 is the simplest. You try one by one. You try one by one. Or maybe just one more example. Say suppose the T3 is a vector, send the R3 to R2, such that I will send the XYZ to X squared YZ, which doesn't seem to be linear. But you can check that T2 will send the 0 to 0. So you need to check other properties. For example, okay, so you can randomly choose. Usually you choose the standard basis will do. So T2, okay, for example, the two vectors I choose will be 1, 0, 0 and 1, 2, 3. 1, 0, 0 and 1, 2, 3, this will give us, okay, 2, 2, 3. 2, 2, 3. So now you evaluate, right? 2 squared, then what is it? So it's the 2 times 3, which is the 4, 6. But if you evaluate separately, 1, 0, 0, this will give you 1 squared, 0 times 0. And this will give you 1 squared, 2 times 3. Right? So it's a 1, 0 plus 1, 6, which is 2, 6. Of course, they are different. Right? So therefore, we can conclude that the T2 is not a linear transformation. So you can see that, okay, again, to verify whether a function is a linear transformation or not, you need to first of all have a conjecture to guess whether there is a linear transformation or it is not. If you believe that it is a linear transformation, try to find the standard matrix. And if you believe that it is not a linear transformation, now you need to see, right? So any one of the three conditions is not fulfilled. So this is the idea to check whether something is a linear transformation. You need to have a conjecture at the very beginning. Okay, maybe let's take a 5 minutes break. Then after that, I'll continue the course and see how much we can go. Yeah. Okay, so far let's continue. So far we see that how a linear transformation is determined by the images at the standard basis. But how about if we use other basis, right? So essentially, right, you may have different bases. Standard basis is just the one of the simplest, but sometimes we may use others, right? So let's see. Suppose that S is any basis for Rn, right? Say V1, V2, Vn. Then, of course, for every vector in Rn, by definition, there is a representation. Say the coordinate vector of the V is of the form C1, C2, Cn. Or in other words, right, this V is, say, C1, V1 plus until the Cn, Vn, right? So this is what we have. Now, okay, now suppose we do have a linear transformation. Then can we say what happens if you know the images at the basis? Indeed the same. TV is of the form T of the linear transformation, which is the linear transformation of the images. And now this one again can be written in the matrix product form. Okay, remember everything is column. So we can write as a matrix whose columns are the TV1 until the TVn, and then multiply with here the C1, C2, Cn. This one is the coordinate vector in the column form. Coordinate vector of the V relative to S. And this is just a matrix, right? Just a matrix. Multiply with the coordinate vector of the V. So again, by any case, if the V is given, this matrix is given, right? So TV is also completely determined by this matrix. TV1, TV2, TVn. Of course, standard matrix will be different, but we know if this T is linear, as long as we know what happens at a basis, then we know the image at any other points. Any other points. So basis is essential. But now the question is, if it is not the standard basis, how do we find the standard matrix? what is the relation between this matrix and the standard matrix for A? Okay, now let's look at it. Okay, some example. Suppose T is a linear transformation. Let's see some example first. Suppose T is a linear transformation from R3 to R4, which is given, it is already given to the linear transformation. Say T111 equals to 1, 3, T of 0, 1, 1 equals to -2. And T of 2, 0, -1 equals to 4, -1. It is already given to be a linear transformation. Okay, now how can you find the standard matrix? Okay, I need to do this first. So first of all, P, right, applying the elementary operation. So I write the 1, 1, 1, 0, 1, 1, 2, 0, -1. I need to ensure that what happens, what is given, right, is a basis for R3. Otherwise, we may not have enough information to determine. Right? So T11, I write in column, first column, second column, and last column, applying the Gaussian elimination. Right? So you can go to the upper triangular matrix with non-zero diagonal entries. Indeed, determinant of the P equals to -1. So P is invertible and therefore, right? So what we are given is a basis. So next, I want to evaluate the standard matrix. So first of all, right? Just use what we did just now. Every vector is uniquely written as a linear combination of the vectors in the basis. So C1 times the U1 plus the C2 times the U2 plus the C3 times the U3, right? So which is, right, just now the matrix P multiplied with the C1, C2, C3. So in other words, if you put the matrix P here, then the vector V is P times the coordinate vector of the V relative to S. So, okay, this is indeed the coordinate vector of the V relative to E. So this P is nothing but the transition matrix from S to E, right? S to E. Okay, now what we want? I want to know what is the C1, C2, C3, right? So we need to solve the following linear system. So apply the Gauss-Jordan elimination. Right, the first term is 3, which is C1. C1 equals to x minus 2y plus 2z. C2 is here and the C3 is here. So in other words, my x, y, z, right, equals to C1 plus here, right? Using the linearity, is the C1 times the image of the 1, 1, 1 plus the C2 times the image of 0, 1, 1 plus C3 times the image of the 2, 0, minus 1. But C1 we know, right? C1 is here, C2 is here, and C3 is here. And just now we are given what are the images of the 1, 1, 1, 0, 1, 1, and 2, 0, minus 1. So the remaining is just the computation. Okay, which I believe you can do. 2x minus y. Then here is the x minus y plus the 3z. Now this can be written easily, right? 2x minus y plus the 0z. This is the x minus the y plus the 3z. So now I can write in the matrix form 2 minus 1, 0, 1 minus 1, 3. Then multiply with x, y, z. So therefore, right? So T is a linear transformation with the standard matrix, which is here. Doable, right? Doable. Just use the definition, which is doable. But looks a little bit complicated, right? So do we have a shortcuts? We always prefer the shortcuts, but there must be a reason to support the arguments. So this leads to the idea of the change of the basis. So suppose X is a basis for Rn, right? Remember? Right, so every vector has the coordinate vector C1, C2, Cn. Then V is in this form, which is, right, the vectors V1, V2, Vn, just not the P, right? Times the coordinate vector of the V relative to S. Okay, so I denote this matrix by P. P are the vectors, right? Whose column P is the matrix whose columns are the vectors in the basis. So here, in this case, P is an invertible matrix, right? So suppose T is a linear transformation from Rn to Rm, right? What is the TV? TV is the linear combination, right? C1 times the TV1 plus until the Cn times the TVn. Well, just now we see, right? It can be written in this form. TV1 until the TVn multiplied with the C1, C2, Cn. Well, this one is the coordinate vector of the V raised to S. Right, these are the images, TV1 until the TVn, right? So, which I denote by B. Of course, this is not the standard matrix. So I can write as a matrix V multiplied with the coordinate vector of the V relative to S. But now let's see. T is a linear transformation, so it must have a standard matrix A such that, right, TV, just okay, TV is AV, right? But TV, just now we see, TV equals to B times the coordinate vector of the V raised to S. But TV equals to AV. How do we compare them? Don't worry. All right, V is P times the coordinate vector of the V relative to S. So I replace this one by P coordinate vector of the V relative to S. Right, so these two are always the same. No matter what is the V and S, no matter what is the coordinate vector of the V relative to S. So therefore, these two matrices must be the same. Okay, so B must be AP. So here is the results. We have a much easier way to find the standard matrix if the images on a basis is given. So suppose S is any basis for Rn, right? Now we write the P as the vectors whose columns are the vectors in the basis. So this P is an invertible matrix, right? And now if T is any linear transformation from the Rn to Rm, you write the B as the matrix, which is M by N, whose columns are the images at the basis, say TV1, TV2 until the TVn. Then we must have the B equals to AP, or equivalently, right? A equals to B times the P inverse, because B equals to AP, right? So you post multiply by P inverse. And this is A. Right, E equals to B times the P inverse. We have a much simple formula, right? So now come back to this question. T is given, right, from R3 to R2. So we can write down, we already see that, right, the given information is a basis. So we just write the P to be the matrix whose column are the vectors in the basis, which is, of course, invertible, right? And the B are the images. So 1, 3, minus 1, 2, 4, minus 1. Now everything is read as column, right? In order to get the A is the B P inverse. So we need to find the P inverse, right? So starting from the PI, we apply the Gauss-Jordan elimination to go to the IP inverse, which is here. So this part is the P inverse. So therefore, my standard matrix A is given by P times the P inverse. Now a simple multiplication shows the first column 2 minus 2 1, second column minus 1 minus 1, third column 0 3. And this is the standard matrix for the linear transformation. Much easier now, right? But you need to have supports, arguments, mathematical reason to support your workings. Okay, so far so good. By the way, is it possible we finish today? Okay, should be possible. Okay, so this is the idea of the change of the basis, right? Okay, so suppose T is a linear transformation and maybe you may have different bases. Right, just now is the standard basis and any basis. What happens if you have S1 is a basis, U1, U2, UN? Right, now we know, right? So TV equals to B times the coordinate vector of the V relative to S1, where B is the matrix whose columns are the TU1 until the TUN. Suppose S2 is another basis in general, right? So TV equals to C, another matrix, times the coordinate vector of the V relative to the S2, where C is this matrix. Now let's compare them. What is the relation? Right, now we can conclude the relation between the B and the C. What is that? Of course, because we have two bases, right? So we need to have the translation matrix. Suppose P is the translation matrix from S1 to S2. Then P inverse is from S2 to S1. So we have, right, coordinate vector of the V related to S1 multiplied by P. This will give you the coordinate vector of the V related to S2. Now what I do? Okay, S2 is here, so I pre-multiply by C. This is what we have, right? I pre-multiply by this. But this is what? This is the TV. This is the same as the TV. And TV is the same as this. So these two are the same. So which is the same as the B multiplied with the coordinate vector of the V related to S1. They are the same thing. Right? They are the same thing. TV, which is this. So now you look at this part. Coordinate vector of V related to S1 related to S1. So these two matrices are the same thing. CP equals to B. Right? B equals to CP. Then, okay, of course, just now what we see, if the S1 equals to S is any basis and S2 is the E, just now the standard basis, right? Then P is the U1, U2, UN, right? Because P is the translation matrix from the S1 to S to E, and the P inverse is the translation matrix from the E to S, and therefore C is just the standard matrix for T. So therefore we have the B equals to C is the AP, or equivalently A equals to the BP inverse. So just now what we discussed is just a special case. And now we have this relation. B equals to CP. They are related in such a way. Okay? So B equals to AP is the what we see just now. This is just a special case by using S1 equals to S and S2 equals to E. You can retry it. Okay, now let's look at very, very special one. Suppose T is just an operator, linear operator from the Rn to Rn. What happens? If it is from Rn to Rn, okay, now let's use the A as the standard matrix for T. Of course, if it is a square matrix. If it is a square matrix, we can do a lot. Okay, let's see. TV equals to AV for every vector V. This is the definition of the standard matrix. And now suppose we have another basis. Say S is any basis, V1, V2, Vn. Now, of course, it's natural to write the matrix P, whose columns are the V1, V2, Vn, which is invertible. P is an invertible matrix. So, and according to the notion, right, the V, every vector V can be written as the P multiplied with the coordinate vector of the V relative to S. But now let's play a little bit. Okay, if I apply the T to this expression. Okay, so if I replace the V, because this is a Rn, so the image is also in Rn. So this is true for every V. So in particular, I can replace the V by TV. Still true, right? Because TV is also in Rn. This is the special thing. So replace, right? This one also replace. So TV equals to P times the coordinate vector of the TV relative to S. But on the other hand, TV is AV, right? But AV, V equals to this, so I can pre-multiply the equation by A to get AV equals to AP coordinate vector of the V relative to S. Okay, this one is just to replace the V by TV. And this step is the pre-multiplication of the A. But these two terms, TV and AV, are the same thing. So consequently, these two are the same. Right, they are the same thing. P times the coordinate vector of the TV relative to S is the same as the AP times the coordinate vector of the V relative to S. Or we can write in this way. Coordinate vector of the TV right to S is given by P inverse AP times the coordinate vector of the V right to S. So this is essentially the change of the basis, right, related to P inverse AP. And if we can choose the S properly, P inverse AP can be a very simple matrix, for example, a diagonal matrix. So this is the idea of the diagonalization. We want to change the basis to make the computation easier. Right? So T can be represented as follows. Right? So if you are given the coordinate vector of the V right to S, then the image will be B times the coordinate vector of the V right to the S, where the B is P inverse AP. So we need to see, okay, which S can make the matrix B simple. Then we use the basis. So for this case, we say A and B are similar matrices. By definition, they are similar. Not just to say they look similar, as long as this relation holds, A and B are known to be similar. Because they are just the different representation matrices relative to different bases. Okay, so for this case, a square matrix is diagonalizable, means it is similar to a diagonal matrix. Okay, so for example, suppose T is this following linear transformation, obviously linear, right? Send the Txy to 0.2x plus 0.2y. Second component is 0.8x plus 0.8y. So the standard matrix, I think everyone can write, right? A is this matrix. And you can easily diagonalize this matrix, which I leave to you. So you can diagonalize the matrix by the matrix P, whose first column is the 1, 4, second column is 1, minus 4, 1, minus 1, with the diagonal entries 1 and 0. So for this case, right, so the S will be the basis. First column is the 1, 4. Second column is the 1, minus 1, right? Because this is my matrix P. Right, so this P is invertible, P inverse times the, okay, this is the standard matrix P, right? This is the D, which is the 1, 0, 0, 0, which is the D. So what does it mean? Now let's look at this. Right, so the T, right, T is given as follows. Looks like a very complicated formula. So if you write the V1 and V2 as follows, so suppose you have write TU equals to V. U and V, I don't care what they are, I just see what are the coordinate vectors. If the coordinate vector of the U relative to S is the xy, then the coordinate vector of the S is given by 1, 0, 0, 1 multiplied by the coordinate vector of the S, which is 1, 0, 0, 1 multiplied with xy, which is just the x0. This is the reason. So if you just look at the coordinate vector relative to the X, you keep the first component and erase the second component. So more precisely, if the linear transformation is written in such a way, right? So every vector in V can be written as C1V1 plus the C2V2. So the T of this image, right? T of the C1X1 plus the C2V2 will only give you C1V1. Now the computation can be much simpler. So this is the idea of the change of the basis. And this is also the idea of the diagonalization. Diagonalization is indeed a change of the basis to make the computation relatively easy. Right? It doesn't mean that you have to follow the XY coordinate system. Especially in Singapore. Okay, you see the map. It's not always upwards is the north. Not always true. Right? Am I right? Because, okay, it will be more convenient. You just see any map in for AS. The north is something, okay, the north is not upwards. The north is somehow different directions so that the map looks nicer. That's it. It's the same. So we may want to change the coordinate system to make the computation easier. If you don't believe, you just download. Okay, now download the AS map. You see the north is not point outwards. Not sure. Okay, so now let's continue. Yeah. Okay, so in particular, a linear transformation is a function. So we see that we can consider some operations on the functions. For example, addition. Addition will be included in tutorial 11, but let's see something more important, which is the composites. Suppose we have two functions, x and okay, maybe I think today the remaining part is straightforward. Okay, let me see, should be able to finish. Yeah, maybe about 10 minutes extension. Yeah. So you don't have to come on Thursday. Okay, let's consider two functions, f from x to y and g from y to z. So here is the picture. Right, f will send the elements in x to y, and the g will send the elements from x to z, y to z. So this is the point x, right, sent to fx, and fx is a point in y, so it can be sent to g. So the result is the g of the fx. So this is the composite. We do the composition from the left, right? So we use this notation, g circle the f, or sometimes you can omit the circle, right? So g circle the f denote the function x to z, so that's, right, you send the element x directly to g composite with the fx. So this is the composite of two functions. Of course, we know that in general, right, composition is not commutative. Then if you come to the linear transformation, because linear transformation, there are also functions. So suppose now we have two functions. S, okay, now this S different purpose. This S I also used as sometimes used as a basis, sometimes used as a linear transformation, but we need to highlight, okay, what is that? So suppose S is a linear transformation from the Rn to Rn, and T is a linear transformation from the Rn to Rk. So again, right, we have the vectors. We have the vector u in Rn, which can be sent by S to Su. Then can be further sent by T to T of the Su, right? So the function mapping on the left. So we can again, right, put the circle sign between them, but pay attention to the order, right? So T circle S, this is the mapping from the Rn to Rk, so that we'll send the U directly to T of the Su. The function is applied on the left. And this is known to be the composite of the composition of the T with the S. And again, of course, because in general, right, there are functions. So T composite with S is not the same as the S composite with the T. But how does it work with the matrices? Okay, let's see first of all, right, what is that? Suppose X is the function, is a linear transformation from R3 to R2. Right, so and T is a linear transformation from the R2 to R3. 2 to 3, right? It's very obvious that they are both linear. So can you find the composites? Of course, yes, but very tedious mapping. Okay, so this is the vector. First bracket for vector, second bracket is for the function, right? But if you do so, okay, I don't like it, but I have to. This is the vector, right? And this one is for the x. And okay, this one is for t. Okay. Can you see clearly? Right, but doesn't matter. So let's do one by one. Split the inside. Okay, s of x, y, z, just copy x plus y, z. Then what is the result? Okay, here the result is three components. The first component is the second one is the z. The second component is the same, and last component is the first component, which is the x plus y, which is as follows. So here is the composites. Okay, yes, this is still simple. We can do in such a way, but in general, the composite will be very complicated. So is it possible that we just go directly with the standard matrices? Okay, of course, here, this one we can write down the standard matrix 0, 0, 1, 0, 0, 1, 1, 1, 0. But how can this standard matrix related to the standard matrices of the S and the T? Is it possible for us to link them? Okay, so here, let's see. Let's see there another way. So this is the mapping. Okay, this is the 1, 1. Okay, this is 1, right? So this is the T composite with S. Now, if you see the S composite with the T, right, we just reverse the order. So first of all, this is the T applying to XY, then apply the S. T applying to XY, this is given by Y, Y, X. Now you look at this. We have two components. The first one is the sum of the first two, is the Y plus the Y. The next one is just copy, so it's the 2Y, X. You can see easily that the standard matrix is the 0, 2, 1, 0. But we want a simple way to find the standard matrix rather than just do this composite. So you can see that the first one, right, the S, the standard matrix will be given as, right, so this is the 1, 1, 0. This is 0, 0, 1. And this is, right, so the first one is the 1, so it's a 0, 1, 0, 1, and 1, 0. So how can these two matrices related to this? Can we do that already? Okay, in general, suppose we have two linear transformations. So that's, okay, the codomain of the first is the same as the domain of the second. So they can take the composites. Here is the picture which I copied from the previous page. So now suppose A is the standard matrix for S and the B is the standard matrix for T. So can we find the standard matrix for the composites? So by definition, SU equals to AU and the TV equals to BV. So now if you are looking for the composites, of course, again, apply to every vector in Rn. So this is, by definition, T applying to SU. SU equals to AU. So you just to have the T applying to AU. But apply to T to AU is just the same as the pre-multiplication of the B. So this is the B times the AU, or we can say it is the matrix BA multiplied with the U. So this is a linear transformation with standard matrix, which is BA. So the composite of two linear transformations is again a linear transformation. And moreover, the standard matrix is just the product of the standard matrix of the two composites. Two components. So here is the results. And now you can see why matrix multiplication is not commutative, because matrix multiplication is essentially the function composites. And we know the composite of functions in general are not commutative. So the matrix multiplication in general, it is also not commutative. They are essentially the same thing. Get it? Okay. So now let's move to the last part, just a few notations. Okay, so namely the ranges and kernels, which are two spaces associated to the linear transformations. Okay, so what are they? First of all, let's see the function. Suppose f is a function. Okay, f is a function from the x to y. So we know that not everything can be matched. Since not everything can be matched, so we only focus on those parts which can be matched. This is known to be the range. The range of the function is the collection of all the images. Okay? So I denote by R. There are many other notations. I use just the capital R. R of F denote the collection of all the images. So for example, okay, this is of course a subset of the R. Now, for example, if you consider the fx equals to x squared parabola, what is the range? The range is just that everything bigger or equals to 0. If you consider the sine function, sine will only go from -1 to 1, right? So the range will be from -1 to 1. These are well known. Of course, we'll not discuss in linear algebra. Let's see what are the ranges for the linear transformations. Suppose T is a linear transformation, right? So now then the range is the same. Linear transformation is a function. So the range of the T is again the set of all the images. So this is the definition. Right, of course, it is a subset of the Rn. But is it a space? We'll see soon. Huh? So for example, if the T is given as follows, first component x plus y, second component y, and last component is x. So now you can see, right, x plus y, yx can be written now as x times a constant multiple, x times 1, 0, 1 plus the y times the 1, 1, 0. So every vector in the image is in this form, which is a linear combination of two vectors, 1, 0, 1 and 1, 1, 0. So in other words, the range of the T, where R of T is the span of these two vectors, 1, 0, 1 and 1, 1, 0, because everything is a linear combination of these two vectors. So at least for this case, the range of the T is a subspace. But now the question is it true in general? Okay, so let's see. Suppose T is a linear transformation from Rn to Rm. And we have any basis for Rn, say V1, V2, Vn. Then for any V, we know that V can be written as a linear combination of the vectors in the basis, say C1, V1 plus until the Cn, Vn. So by linearity, TV is in this form, right? By linearity. And so the TV is determined by the images, right? It is determined by the images. And of course, which is a linear combination. So it belongs to the span of the TV1, TV2 until the TVN. So the range is a subset of the span of the TV1, TV2, TVN. And indeed, the converse is also true. Okay, if you consider a linear combination of the TV1, TV2, TVN, which is in this form. But now again, using the linearity, it is an image of a single vector C1V1 plus until the CNVN. So this belongs to the image because it is the T of something. It is the image of this vector. So therefore, they are the same thing. Right, the span of the TV1 until the TVN is a subset of the range. So therefore, this is not only just a subset, they are equal. So here is the results. Suppose T is a linear transformation, then the range is a subspace of the Rm. To be more precise, it is the span of the TV1, TV2, TVN, where the V1, V2, Vn is any basis. In particular, you can use the standard basis, but any basis will do. So the range is always a subspace. Note that T has the standard matrix A, right? It has a standard matrix A in particular. So the columns are the TE1, TE2, TEn. So the range of the T is the span of the T1, T2, Tn, but these are the columns of the A. So the range of the T is nothing but the column space of the standard matrix. Okay, very simple arguments. So that's good. Okay, so we want to have more definitions, right? So we want to have more definitions. Say suppose T is a linear transformation. So because it's a space, so we can determine the dimension. So the dimension is known to be the rank of the linear transformation. We know that's right. Just now we say if A is the standard matrix for T, so the range of the T is the column space of the A. So the rank of the T is the same as the rank of the A. They are the same thing. The rank of the A and the rank of the T, they are the same thing because the A represents the linear transformation. Very simple notion. So for example, right, just now the thing, right, T of the xy equals to x plus y, y, x. So you can easily write down the standard matrix for T, which is the first column 1, 0, 1, second column 1, 1, 0. So now can immediately say that the range of the T is the span of the column of the A because it is just the column space of the A, span of the 1, 0, 1 and 1, 1, 0. And moreover, it's very easy to see the rank of the A is 2 because the two columns are linearly independent. So the rank of the T is the same as the rank of the A, which is 2. So all the questions about the linear transformations can be changed to the problems of the matrix operations. Okay, so far so good. So another example. Okay, what I can say I can do faster because these are just the examples. So this looks very complicated, right? Looks very complicated, but we can write down the standard matrix. Once you get the standard matrix, you see, right? There are 4. No W, no W means okay, 0 here. So this is the standard matrix for T. So what are the images? Okay, the collection of all the images is just the span of the columns of the standard matrix. But 0, 0, you can ignore, right? So the RT is the span of these 4 vectors. But how do we find the basis for the range? It's the same as finding the basis for this vector space, right? 1, 2, 3, 4. So how do we do that? Apply the, which one? So this is already in columns, right? So what to do? Gaussian elimination will do. Apply the, okay, why I use Gauss-Jordan? Gaussian, should be Gaussian, this is not Gauss-Jordan, Gaussian. Typo, Gaussian. Apply the Gaussian elimination, you come to here already. So pivot points. So these two columns are linearly independent. They form a basis for the column space of this. So therefore, these two vectors, they form a basis for the column space. Right, pivot points. So pivot points, right, coming to here, these two columns. So therefore, we can say the range of the T is simply spanned by the first column and the second column and third column of the standard matrix. So the rank of the T is the dimension of the range, which is 2. So you can see it is essentially again the matrix operation. Okay, find the standard matrix. Then everything you deal with the standard matrix. So this is one, okay, then this is one way. You can try another way because we never say that we must keep the columns. You can consider the transpose, view everything as the row matrix. Now apply, here I apply the Gauss-Jordan because I want the matrix to be simple enough. So here we have, okay, non-zero row. So these two rows will also span the range, right? So these two non-zero rows. So therefore, but we still put in columns. So the range is the span of these two vectors. Say the basis is not unique. The basis is not unique. You may have different ways to get the basis. Rows or column, up to you. Now, sometimes depends on the question. Okay, so for the same reason, right? The range of the T equals to 2, which is the dimension. So this is one space associated to the standard, associated to the vector space. Associated to a linear transformation. Let's see another one. Okay, this is different from the very general function. So we just focus on the linear transformation. For linear transformation, the only thing we are sure is you send the 0 to 0. Right? We have the 0 vector in Rn, we have the 0 vector in Rm, you send the 0 to 0. So for such a case, we want to check, do we have other vectors which can also be sent to 0? But at least the one single one. Maybe the whole thing, but maybe just the one. So we just consider all the vectors in Rn which can be sent to 0, and this part is going to be the kernel of the linear transformation. The collection of all the vectors which are sent to 0. Of course, at least they contain the 0 vector. but maybe the whole of the Rn, we don't know, right? So by definition, it is the collection of all the vectors which can be sent to 0, and in particular, of course, it is a subset of the Rn. But we are more interested to know whether it is a subspace. Is it space? Should be, right? Otherwise, it doesn't worth to introduce. So we call that T0 is 0, right? So we know that the kernel will contain at least the 0 vector. Okay, so for this case, right, so coming to the same T1. So let's find the kernel of the T1. So what to do? If you want to find the kernel of the T1, this is just to let the T1 of the x, y, z equals to 0. So essentially, I want this part to be 0. And what is that? A linear system in 3 variables and 4 equations. Right, so essentially, we are looking for this. But this is a homogeneous linear system. So what we are supposed to do is to apply the Gauss-Jordan elimination, right? Apply the Gauss-Jordan elimination, you can see that all the points are pivot, all the columns are pivots. So what does it mean? Only the trivial solution, right? Only the trivial solution. So the kernel is just the, 0 space. How if you consider T2? T2 is this function, right? Find the kernel. So again, we do the same thing. T2 applying to x, y, z will give you 0, 0, 0, which is first component z minus y, last component x. So, but this one we can solve easily. Z minus y, z and y are the same, x equal to 0. So we set this one to be parameter. So it is, say, x equal to 0, others are tt. So it's a scalar multiple of 0, 1, 1. So therefore, right, the kernel is the collection of all the vectors in the form 0, y, y, which is the span of 0, 1, 1. So in particular, for this case, it is also a vector space. So is this true that in general, the kernel is a vector space? Should be, right? Again, we refer to the standard matrix. Suppose T is a linear transformation with the standard matrix A, then TV equals to AV. Now we are looking for the collection of all the points so that TV equals to 0 is the same to say we are looking for all the vectors so that AV equals to 0. But this is the homogeneous linear system. The solution set is the null space of the A. So everything related to the standard matrix. So the kernel is nothing but the null space of the A. The range is nothing but the column space of the A. So now we have the summary. Okay, I just put together. T is the linear transformation with standard matrix A, so the kernel of the T is the null space of the A. And so because it's a vector space, we can define the dimension, which is known to be the nullity. Now, of course, the nullity of the T is the same as the nullity of the A, right? They're the same thing. And the rank of the T is also the same as the rank of the A. So everything related to the standard matrix. Don't just play with the linear transformation, play with the matrix. So the remaining are just a few examples, right? So suppose T1 is this mapping. Now we are ready to consider, all right, just now we have the T1, right, kernel of the T1. This is the mapping. We just to see what is the kernel of, say, 2, minus 1, 0, 1, minus 1, 3, minus 5, 1, 0, and 1, 0, minus 1. Now we see the, null space of this matrix is 0, 0, 0. So the kernel of the T1 is the 0 space. Then consequently, the nullity of the T1 equals to 0. And similar for this one, right? Just now we see the kernel of the T2 is 0, 1, 1. Indeed, you just need to see what is the null space of, here is the 0, minus 1, 1, 0, 0, 0, and 1, 0, 0. Right? And we see that the kernel of the T2 is the span of 0, 1, 1. So the nullity equals to 1. Right, these are the examples. Okay, for just one more. Say suppose T is defined as follows. Right, so now we don't need to write down the equations. We just need to get the standard matrix. We need to play with so many symbols. It's a waste of time. So A is this matrix, and now we have apply the Gauss-Jordan relation because we want to solve the system, then Gauss-Jordan. If you just want to determine whether it's a row, whether it is a basis or not, then Gaussian will be enough. So Gauss-Jordan relation go to the reduced direction form, right? Now you can see. You can solve, right? This is a parameter, this is another parameter. So let W and T be arbitrary parameters. So the X will be minus 3T and the Y equals to T. Right? So therefore, we have X equals to minus 3T, Y equals to T, then the kernel is of this form. Then clearly you can separate the S and T to have X times 1, 0, 0, 0, then plus the T times 0, minus 3, 1, 1. Right? So therefore, the kernel is the span of these two vectors. And therefore, the nullity of the T equals to 2, which is also the same as the nullity of the A. Okay, just one more remark. So some properties summarize. Suppose T is a linear transformation. I hope it's not rushed, actually. It's just related to matrix. Once we get the standard matrix, change the linear transformation to the matrix, then everything is known. So suppose T is a linear transformation. Let A be the standard matrix for T, right? A is an n by n matrix, so that TV equals to AB. This is our definition. So we already verified that the range of the T is the column space of the A, and consequently, they have the same rank. And we also see that the kernel of the T is the null space of the A, and thus they have the same nullity, the dimension. So recall, we have the dimension theorem for matrices. Say for any matrix A, rank of the A plus the nullity of the A is the number of the columns of the A. For this case, A is n by n, so this is n, right? And the dimension theorem for linear transformation, we just copy it. Rank of the T is the rank of the A, nullity of the T is the nullity of the A. So we see the rank of the T plus the nullity of the T equals to n. N is the dimension of the domain. So now you can see, we link the linear transformation to the matrices. Of course, this is just a linear transformation between the Euclidean spaces. So in the future, you may need to study the linear transformations between non-Euclidean spaces. Then the working will be more complicated. Okay, I think that's all for the lectures. And other times I will see when I can arrange for the consultations as well. And don't forget that we still have the tutorials to run per euro. Okay, that's all for our lectures. And okay, just wait for our announcement and some of the lessons I'll arrange for the consultations. Okay. Okay, see you and enjoy.